Hold a penny in your hand. It's light, familiar, and, ironically, worth less than it costs to make. Behind that little coin sits a nation-scale machine. Encrypted design rooms, robotic metallurgy lines, AI-assisted presses thundering at hundreds of strikes per minute, and autonomous pallets rolling through facilities that look more like chip fabs than old-world mints. America still produces billions of coins a year in 4 fortress-like sites: Philadelphia, Denver, San Francisco, and West Point. Yet the very technologies that perfected coinage are lining up to retire it. How U.S. coins are made today. It starts with a sketch and ends with a signature of light. The life of a modern coin is a ballet of design, metallurgy, mechanics, and machine intelligence, every stage timed to milliseconds and measured in microns. Digital design and simulation. Every coin begins in the U.S. Mint's design studios, where artists and engravers use CAD and high-resolution sculpting software to model portraits, eagles, shields, states, parks, whatever Congress has authorized. The digital model isn't just a pretty picture, it's a relief map with depth profiles, rim geometry, and flow lines that dictate how metal will move under hundreds of tons of pressure. Designers run finite element simulations to predict strike fidelity, letter sharpness, and die wear. Subtle tweaks, raising a cheekbone by 0.05 millimeters, thickening a serif, softening a fold in drapery, can determine whether millions of coins emerge crisp or mushy. Once approved, the model is cut or laser milled into a master hub, from which master dies and working dies are created, each die a mirror image stamp of the art that must survive hundreds of thousands of strikes. Automated metallurgy. Meanwhile, the raw material becomes something coinable. The U.S. uses specific alloys for each denomination: cent, penny, a zinc core with a thin copper plating, nickel, a cupric-nickel blend, approximately 25% nickel, 75% copper, dime, quarter, half, copper-nickel, clad, 2 bright copper-nickel faces bonded to a copper core, the distinctive sandwich, bullion and commemoratives, silver or gold at West Point/San Francisco, smart pressing and AI quality control. Now the thunder. High-speed coinage presses, think Schuler or Grabiner giants, slam hardened dies into planchets at up to approximately 750 coins per minute, each strike delivering hundreds of tons of force. In one motion, the obverse die front and reverse die back transfer the art. A collar constrains the edge, creating reading on dimes got quarters. The planche flows plastically, filling the highest relief. Robotic packaging and full traceability. Fresh coins ride conveyors into autonomous counting lines. Weigh cells, inductive sensors, and RFID gates tally and verify each batch before robotic palletizers stack boxes for armored transport. Every batch receives a digital pedigree, lot number, press ID, die set, shift time, and QC metrics. A cradle-to-vault data chain that ties back to raw coil and forward to Federal Reserve distribution. Why a perfect mint still makes imperfect sense. If everything is so precise, why are coins on the chopping block? 3 pressures, cost, logistics, and behavior, are squeezing physical change out of everyday life. The cost problem. Seigniorage in reverse. Seigniorage is the profit a government makes minting money, the face value minus the production cost. For high-value coins, that math works. For low-value coins, it flips. The 1-cent coin has long cost more than a cent to produce when you add metal, energy, labor, shipping, and overhead. The 5-cent coin has spent years on the margin. That means the mint can strike billions of coins and still lose money on certain denominations. Seigniorage in reverse. Why not change metals? Alloy tweaks are tightly constrained by vending, coin acceptor compatibility, electromagnetic signature, and public expectations. Shift too far, and you break parking meters, laundry machines, transit devices, and bank sorters nationwide. Every composition change triggers multi-industry re-engineering, which costs billions and takes years. The distribution problem, moving mountains of metal. Coins are heavy. The mint strikes them, but the Federal Reserve and armored carriers must warehouse, ship, and recirculate them through thousands of banks and retailers. That takes diesel, drivers, depots, and time. In normal times, coins meander through the economy in predictable loops, cash drawers to pockets, to coin jars, to Coinstar/branch lobbies, to vaults, to back to stores. But when loops break, as during the pandemic coin circulation disruption, shortages appear despite warehouses full of coins. The system isn't short of metal, it's short of motion. The response is expensive: expedited shipments, incentives to return coins, rebalancing regional flows, all to move low-value units that many people no longer need. The future of physical coins. AI-directed minting. Algorithms as monetary quartermasters. In the old world, coin demand forecasts relied on historical patterns, seasonality, and reports from Federal Reserve banks. In the new world, AI ingests real-time retail data, POS transaction mix, transit usage, vending telemetry, coin recycler inventories, and macro signals, fuel prices, tourism flows, disaster declarations. Instead of strike X billion quarters this year, an adaptive algorithm will recommend dynamic minting schedules city by city, week by week. Add predictive withdrawal. The same models watch wear signatures and circulation decay to trigger targeted retrieval of old coins, much like predictive maintenance, but for national coin stock. The result is a shrinking, smarter coin pool, far fewer coins, far more precisely circulated, with lower logistics burn. If the US keeps any coins at all, expect AI to be their invisible manager, squeezing waste out of every mile. Digital twins, rehearsing money before metal. Before future presses ever stamp a die, digital twins will simulate the entire coin lifecycle. A coin design is loaded into a physics-grade model that predicts strike fill, die wear, edge integrity, reading fidelity, scanner readability, even clad delamination risk. The twin then runs the supply chain in simulation. How many blanks are needed? Which plants optimize energy use? How regional distribution affects recirculation and recycling? Change a single parameter, rim height, alloy blend, die hardness, and the twin updates cost, seigniorage, defect rates, and machine downtime. We already do this for jet engines and wind farms. Applying it to coinage makes minting nearly zero waste and near zero surprise. It also answers a harder question. What if we don't mint this coin? The twin can show the behavioral impact, rounding at checkout, cash handling costs, and equity effects on cash-dependent households. Programmable money, from metal rules to code rules. Even as coins reach peak efficiency, payments are leaving hardware altogether. The Federal Reserve and peer central banks continue exploring digital currency models, call it a CBDC or a digital dollar, alongside the private instant payment rails growing today. Two big design forks shape the future: account-based versus token-based. Account-based models look like a public version of today's bank ledger. Token-based models behave more like digital cash, cryptographically signed and transferable peer-to-peer. Direct versus intermediated distribution. A direct model means consumers hold balances with the central bank. An intermediated model lets banks and fintechs distribute and manage wallets under common rules. The fall of coins, international signals, and US scenarios. Look abroad for the time machine. Sweden operates near cashless, with citizens using Swish and contactless for nearly everything. Some enthusiasts even tried implanted NFC chips. South Korea has spent years reducing coin usage, encouraging change to card programs rather than physical change. Beyond coins, the new payments, body plan. If metal fades, what replaces its function? Biometrics and frictionless pay. Face/voice/fingerprint already unlock phones and authorize taps. Next-gen sensors enable risk-based authentication. Small purchases flow with a glance. Larger ones prompt a second factor. This preserves speed without sacrificing security and reduces the "I forgot my wallet" problem to "I forgot my face," which is unlikely. Tappables, wearables, and kinetic cards. NFC rings, watch bands, even passive kinetic cards, powered by motion, turn payment into gesture. Transit systems, arenas, and quick-serve retail love this because queues vanish and fraud stays low. Offline digital cash. To replace coins' resilience, we'll see secure offline wallets, hardware or phone-based, capable of local, signed transfers that sync when connectivity returns. Think of it as mesh money for storms, rural zones, or blackouts. No bank needed, cryptographic integrity intact. When metal meets code. So, will coins still exist in 20 years? Probably, but smaller, smarter, and rarer. A reduced denomination set managed by AI, simulated by digital twins, and minted as much for resilience and ritual as for daily commerce. Their everyday role? Replaced by biometrics, tappables, instant rails, and offline-capable digital cash that preserves the inclusivity and privacy we value in metal. And if we get this right, the paradox flips. The same technology that perfected coins will retire them gracefully, while building a payment system that is faster, fairer, greener, and harder to break.